You're still muted?
And yes, I should be unmuted now, and I hope my slides are showing.
Yes, perfect.
Okay, perfect, fantastic, thanks. And there's nothing blocked at the top, right?
No, it's just like the white Schrödinger slide.
Perfect, fantastic. Okay, thank you very much for the nice introduction. And then also I want to say thank you for organizing this event and the fantastic talks that we've had so far. So today I'm going to talk about a application case study, at least mainly that is in the field of biosurfactant formulations, where we're trying to combine automated simulation workflows, molecular dynamics workflows, and machine learning approaches. But before jumping into that, I just very briefly like to introduce Schrödinger and also myself. So our company's mission is to transform in a way the way how new medicines and materials are discovered, and we try to do that through developing advanced computational methods. So we are working on developing simulation platforms, digital research platforms, and then also applying those together with our partners and customers. So I myself, I'm leading our applications team for material science within Europe, and so I'm usually located in our Mannheim office. And yes, so the digital approach that I want to talk about a little bit today, and an application study that we are running at the moment in the area of formulations. So I thought that would fit quite well for today. But first of all, so what we're envisioning here, and that's I think come up multiple times today, and also especially in the previous presentation. But a big topic in driving materials research is of course screening large chemical spaces, large material spaces, for optimal solutions. And one traditional way would be to create a structure library using high-throughput simulations, for potentially physics-based simulations, quantum mechanics, molecular dynamics, coarse grain, mesoscale, et cetera, up the length scales, and then to select top candidates for the synthesis and maybe reiterate in that loop. What we try to do here is to enable this design platform with machine learning. So we've heard in the previous presentation very nicely as well. The design spaces are very big, and very often, especially in the case of formulations, we can't necessarily approach everything with physics-based simulations. So we here we try to use data that we've derived from physics-based simulation for part of our data set. We label that data for machine learning approaches, learn structure property, mixture property relationships, predict then new structural components or new structural materials. And then we score those. We can go directly to synthesis, or we can revalidate the physics. So that's a kind of process that we are also applying to a formulations case study at the moment. One thing that I'm not going to talk about today, but please contact me if you're interested in more detail. We're also working on active learning loops here to close that loop and really go in iterations where we select that small set of structures, we build these machine learning models, and then we improve them based on our quantities that we need to optimize and where we need to find an optimal parameter set for. And so that's indicated by that dotted line. So that's also something where we're active in these active learning workflows to iterate them through physics-based and machine learning to make sure that the models that we're learning are really capturing the necessary feature spaces. But at the same time, we avoid the necessity to really screen with explicit physics-based simulation on the whole design space. Okay, so what we are working on then has basically 3 pillars, and I'm trying to touch upon each of those a little bit. So physics-based modeling, we've heard a lot about that today already. Things like quantum chemistry, molecular dynamics, etc. What's of course important here is to develop automated workflows to make that easily accessible and then also reproducible. Then machine learning, for example, structure property or mixture property relationships, just to speed up the screening of large chemical spaces. It's not going to be a topic today, but we are also active in deriving de novo design and generative models. So where we really, instead of screening a preset space, the algorithm comes up with new suggestions and tries to optimize that with different procedures. And then one pillar that we also strongly believe that is really necessary to make this kind of digital research successful, especially in a commercial setting, is then what we call here the team-based intelligence and collaborative informatics. So platforms that enable to really the digital and experimental results to be viewed side by side on equal footing, and in a way that is accessible and understandable to both experimental and theoretical scientists. And then also the facilitation of collaboration whenever teams are split across different locations, geographies, different teams, time zones, etc. I think we're all familiar with the challenges of that nowadays. So we really need platforms where we can bring that together. And then also from the modeling perspective, such platforms can provide then also an easy access to well-defined, controlled, reproducible models that have been devised for a certain project and then stay consistent and controlled over the course of a certain project. So I'm going to try to sort of touch upon all of these a little bit. Okay, so high throughput screening, we have over the course of time done different kinds of studies. As an example, I'm bringing here one for polymers, just very briefly as a summary. This was published about a year ago as well. So we did here a molecular dynamics large-scale high-throughput mega run, where we screened the glass transition temperatures of a bit more than 300 polymers using an automated workflow that we pre-built that takes the different polymer chains or the monomers, built up polymer chains, puts them into simulation box. We have ways of growing the polymers in an entangled way with Monte Carlo-based approaches, relaxing that with molecular dynamics, and then running a cooling protocol to get the density versus temperature plots and extracting then with an automatic fit to that the glass transition temperature. For this study, we used our molecular dynamics engine, Desmond, which is running on GPUs, and our force field, the version that was up to date back then, that was OPLS-3E. We are constantly expanding our atomistic force field to include wider and wider molecule and materials ranges. So here a plot of the results that we get for calculated versus experimental glass transition temperatures. We see a very good ranking, especially of the glass transition temperatures for these polymers. The color code gives a standard deviation of the different evaluations. So because we're running 10 replicates and we're sampling at each point here, we can do quite a bit of statistics and then come up with a standard deviation that gives us a little bit how a measure for how reliable we think based on the simulation the result is. So with that, in this case, in case you're interested, so that was a compute time on a single GPU of about 10 years. For, yeah, with the 10 replicates, that was like more than 3,000 simulations that were run from beginning to end. And then by really parallelizing that and plot resources, we got that simulation down. So that is something that similar studies we've done in different areas. So one goal of the study that we are currently doing, and which I would like to present, is on the one hand to apply our tools to biosurfactants-based formulations, but also to see how we can use the data from these screenings that we do with molecular dynamics in machine learning approaches afterwards, and whether we are able to build a good machine learning models for these formulation-based properties based on our simulated data. And before I begin, I want to say that most of the calculations were run by my colleague Ben Koskia from our simulation science team, and so I'm very grateful for him to run these, and want to give credit to his work here. So biosurfactants, of course, very active area of research as eco-friendly alternatives to formulation ingredients, wide range of application areas, mainly in detergents, soaps, etc. There's of course a high consumer appeal, renewable, biodegradable. They often even have a competitive performance in that they are milder, but still have a comparable performance to existing surfactants. And one bottleneck that has existed is the large-scale production, but it seems with recent biotechnological developments and also different directed methods, and that barrier seems to be at least lowered in recent times, making wider ranges of biosurfactants and also in larger scales available. So basically, some microorganisms need to ferment oils or sugars, and based on those, produce then the biosurfactants. There are different classes of biosurfactants. The one that we are focusing on in this study is rhamnolipids. There are also phosphorolipids, surfactants, and others. But here for the initial study, we are focusing here on rhamnolipids. And there are different design parameters that are available on the experimental side. The lipids can be modulated in tail length, they can be cyclic versus linear setups, there's concentration, mixture, parameters, co-surfactants, salt concentration, solution pH, temperature, etc., etc. So for this initial study, we decided to start with a defined chemical space and also a processing mixture space that is summarized here. A reference down here is a review of rhamnolipids that are accessible through known and accessible through biotechnological approaches. And we are focusing here in the design space on anything that is available and described in this paper, but the basic design space with these rhamnolipids, we have a rhamnose unit and a lipid unit, and then there's can be monorhamnose, where there's one rhamnose unit, or dirhamnolipids. We have two rhamnose units, and then similarly we have either monolipids here on the left, or we have dilipids with two lipid units. The design space we went with at first to apply our workflows is varying on the one hand the concentrations, so starting with 5 weight% and going up to 15 weight% in our aqueous solution. The lipid tail length, so we are varying the length of these lipid tails here. And then one effect that is very strong on these formulation properties is typically the pH. So depending whether these are protonated or deprotonated at the acidic unit up here, we get very different properties. So that's another effect we wanted to include right in this initial study. So we are looking at three sort of model setups. One is low pH and fully protonated. Then we are looking at half protonated, so pH equals pKa. And then one fully deprotonated, resembling high pH conditions. The pH or the pKa for these types of systems is somewhere typically between 4 and 5. And from this design space, we chose every type of rhamnolipid that is being described as existing and accessible. So in total, that added up to about 150 total systems. Okay, so our simulation setup, we use here molecular dynamics workflows. We are especially interested into the aggregation behavior and the behavior of these surfactants in aqueous solutions. With each of these rhamnolipids, we build the molecular structure, and then we place those into a simulation box. We always keep the number of biosurfactants per box constant. So we always have 100 of biosurfactant molecules per simulation box. We chose this because we are primarily interested in the trends in aggregation. To really see, even though the absolute sizes of the aggregates, of course, dependent on the amount of biosurfactant also available in the simulation box, what we especially want to see the trends between the different conditions and biosurfactants. So we kept the number in this case constant at 100, and then filled the simulation box up with water in order to achieve the targeted weight percent. These simulation boxes here, for example, for one of the dirhamno-dilipids, and to have better visualization, the waters are hidden here, so we are only showing the rhamnolipid in the simulation box. And so we first run some equilibration protocols that we apply routinely, a series of some Brownian relaxation, molecular dynamics at low temperature, then going up to high temperature. We equilibrate at constant pressure, constant temperature. And from that equilibration, we sort of average the volume of the simulation box. And then we run a 100 nanosecond simulation at constant volume. And the trajectory that I'm showing here, I hope the video is coming through, that is showing those 100 nanoseconds production run for the molecular dynamics. So I think I need to switch the laser pointer off, yes, to go to different stages here. So in the beginning, we still have smaller aggregates here, and they get a little bit bigger over the simulation time. And then at the end of these 100 nanoseconds, we end up for this concentration and the protonated forms at low pH conditions with a few relatively spherical aggregates in the system. So we're going to stay with this lipid for the moment and increase the weight percentage. So this is an example for 15 weight percent. So if we run this, again, the 100 nanosecond production run to look at the aggregation behavior. So here we see that over the course of these 100 nanoseconds, we have here a more complex aggregate forming. It's sort of a worm-like aggregate at this higher weight percent, still at low pH conditions, so fully protonated. And then at the end of our simulation, we sort of have that worm-like aggregate forming in a quite stable way. Again, because we're keeping the number of biosurfactants constant within the simulation box, the total size and the total shape might sometimes change when we sort of include larger systems. But what we're really interested in is the trends, for example, when going from these low pH conditions to high pH conditions, what does that do with the relative trend? So what does that do with our aggregates? And then if you look at this, oops, let's see. Why can't I play this video? Okay, there it's coming through. So here in this case at high pH, where we have the deprotonated form, the sodium as counter ion, we have electrostatic repulsion between the head groups. And thus we have then, and that's also seen experimentally, when deprotonating, usually that increases the disorder in these systems, and then basically leads to the breaking up of larger structures that have been formed in solution, and leading to more micellar structures instead of these larger, more complex aggregates at low pH. So that's basically, from a qualitative point of view, structural, what we would also expect from experiment for such a series of simulation. So that's already great. And so the next step is then to think about, okay, what kind of observables from experiments, so how can we bridge here between simulation and experiment? What would make sense to look at in our machine learning model to see whether that we can get useful models out of such molecular dynamics lens. So I have here different experimental observables like critical Neisser concentration, forming behavior, viscosity, morphology, etc., etc. They correlate with different types of properties that can be derived from modeling. So for example, for critical Neisser concentration, forming behavior, the surface tension is a property that can be accessed in simulation and is correlating with them. So surface tension was the next thing we looked at. So we introduced a vacuum space in the simulation box to create an interface between our mixture and vacuum. Equilibrated that again with 50 nanoseconds, and then extracted the surface tension based on the pressure tensor. Here we show some results for this rhamnol dilipid here. So in all the cases, we usually get a aggregation and interface, and then also some of the biosurfactants staying in solution. What we can see here is also with protonated mixed to deprotonated, we see here some trends where with the protonated, we would expect here lower critical Neisser concentrations because we have easy aggregation. So for that concentration range, we already have a plateau of the surface tension, while for the deprotonated in green, where we expect a higher critical Neisser concentration, here we still see a drop of the surface tension with the weight percent surfactant. So from the trends and the qualitative trends that we want to extract here, so that corresponds to what we would expect for such systems. So that is one thing that we extracted. Then viscosity, we used here our workflow that we've implemented for extracting shear viscosity based on the green Kubo integral. So we are integrating the pressure tensor autocorrelation function. For this case here, to obtain the shear viscosity, the plot here on the top left corner is showing the viscosity trend with the weight percent biosurfactant. This is averaging actually over all the systems and all the conditions at 5 weight percents, all pHs, all dirhamnolipids, and 10 replicates each. And sort of the bars here, they give an indication of the spread of values, but we still, even when averaging over these systems, we see we have a strong trend with the weight percent. And when we zoom in at 15 weight percent, we can look at trends for the pH, and we can then zoom in again. So if we zoom in at high pH, so we zoom in into that data point, then we get sort of the different rhamnolipids at that pH value. So we can analyze that. So that is an analysis we looked into. We didn't look into cloud point itself, but what is important for the cloud point is, of course, the size of the different aggregates in the solution. So we are analyzing those. And what we get is a wide range of different system or of different aggregate sizes, depending on the conditions, the size of the systems, etc. So that is also the radius of gyration is one parameter that we transported further into our machine learning approach. And then the morphology, that's of course also important. Is it more spherical, micelles, or more worm-like aggregates? So here we look at the eccentricity. So how different is it from a spherical shape, or also the ratio of the longest versus the shortest axis. So here we have, for example, a very long axis in one direction and in the other direction a short one. So that would give us a big ratio here. So we took our molecular dynamics-based screening that we obtained so far for these 150 systems and conditions. We featureize our biosurfactants using molecular descriptors from RDKit and Morgan fingerprints. So in total, it's about 1,000 features. And then we apply here different regression models. We didn't list all of them here, but it's a larger set of different regression models. And then we look at different formulation properties. I have number of clusters and largest cluster as a little bit more detailed example here. So in the top panel, we have from the molecular dynamics, sort of the range of values we're looking into here. So these, how many molecules do we have in the largest aggregate, and how many aggregates do we have in our simulation box? And that averaged over a certain time of the simulation. And then we take these values, we take our design space here, or feature space, and then we come to different models. So depending on the property, different models perform better than others. So in the case of the number of clusters, this XGBoost, so it's a gradient boosting technology, so that performed best, while in the case of the largest cluster, in this case, a random forest was performing best. But we would get very good training and test set R² values on these. And if we look at the whole set of different properties, so then we get here an impression. So we looked in this plot here at the number of clusters, surface tension, largest cluster, radius of gyration, eccentricity, so that's sort of the deviation from the spherical micelle. And this is sort of the one that is weakest in performance. So that's around the test R² around 0.5. That's sort of the ratio of the different axes within the structures. But overall, we are very happy to see these correlations for these properties in general. And we're further continuing to expand this. And just very, very briefly at the end, what does it look like if we want to bring this together and enable this research in a collaborative environment? This is a screenshot from a web page based application called Live Design that we're developing. And what we have in this case is here the data set that's been uploaded by Ben in this case here. We're showing the structures, names, etc., different properties. And then we could have here different preset simulation workflows or upload the data. And so we have here, for example, simulated viscosity, predicted surface tension. This would be a machine learned model that has been uploaded here. So whenever drawing a new structure, making modifications, that we can then, on the one hand, keep track of it, make it available to our different teams working in different locations. Ben is located on the West Coast in the US. And then also have different workflows and machine learned models for such projects in one place to apply them. So that is sort of closing the circle of the different pillars for applying such projects and handling then the data also that come up in these projects. And with that, I'm at the end of my presentation, and I want to thank you for the attention. And are there any questions?
Yeah, thank you. There are already a couple of questions in the chat. Mm-hmm. So let's start with Joanne Cook. She asks how long these simulations take, and she's talking about the rhamnolipid micellation simulations there to get 100 nanoseconds, and were they run on CPUs or GPUs?
Mm-hmm. Oh, that's a wonderful question. So the system size was here between 30,000 and 300,000 atoms per simulation box, depending on the type of lipid and then the weight % concentration. So the total simulation time for running everything for one structure was between 12 hours and 5 days, depending on the system size. And we run those on GPUs.
Okay. The next question is from Alessandro Patti, and the question is, the values of shear viscosity at different pH seem to be within the error bar and difficult to distinguish. Possibly this uncertainty is due to the noise associated to the use of Green-Kubo equations. Have you considered to calculate the shear viscosity with out of equilibrium MD simulations?
Yes, that is something that we are definitely considering. And so they are still averaged also over different rhamnolipids. So the pH dependence was not for one rhamnolipid. So that also creates an additional noise in that specific graph. But that point is very valid, and that is something we are exploring.
And regarding to the pH, there is also a question from Paola Carbona. Mm-hmm. Were these simulations actually run at constant pH simulation. So where these run as constant pH in these simulations. Okay.
Yes, that's sorry, no, not constant pH, so constant protonation states. So we assume constant protonation states, and we say this is sort of like extremes of the pH, like low pH, high pH, and then exactly at a pH where we assume 50-50. But it's constant protonation state, sorry, yes.
Okay, and yeah, Paula also commented that out of equilibrium simulations might break the microstructure. So maybe something to look out for in the future.
Exactly. So that is definitely something that additional effect that comes in when going to the non-equilibrium one. So we started with the equilibrium here, and but it's a very valid point that we're also exploring.
Yeah, and this brings us then back to the other talks we had today about worm-like micelles rapturing and all that. So I think that's a nice point to close. There are also no more questions in the chat.